And out of these 20 are for average and 20 for regular size. These seats will
Good morning to all of you. Let us now discuss the remaining part of the convolutional codes. So I was discussing about the trellis diagram, and I will explain once again the trellis diagram, that how the trellis diagram is drawn with the help of an example. All right. So let, as I will just introduce you to the trellis. Just give me a minute, please. I'm actually referring to. Okay, so we can start from here. Okay, so trellis diagram is an extension actually of the tree diagram, where I said if you look at the tree diagram, after the constraint length in the encoder structure that we were discussing, I'm using the same encoder structure for all the explanations. So in that encoder structure, the constraint length was 3. So constraint length was 3 means 3 time intervals, 1, 2, and 3. After the third time interval, you will see that the structure, uh, this is time T1, T2, and T3. At this point, you will see that after the third stage passes, the next stage, if you look at the upper portion of the tree diagram and the lower portion of the tree diagram, so the upper and the lower portion are identical and they are repeating basically. So what I proposed was that we will merge the upper portion with the lower portion with corresponding branches. So a new structure that results, and that structure is called as the trellis diagram, right? So how to go about the trellis diagram? We have 4 states, 0, 0, 1, 0, 0, 1, 1, 1. You can write, as I said, you can write the states as per your choice. So this bold line, uh, it is represented in this diagram with red and blue color also, but there is only one distinction is required. One distinction is sufficient, meaning by I can represent an input of 0 with bold line and an input of 1 with a dotted line, right? So that clearly tells me that whether the input bit is 0 or input bit is 1. So this is the initial state. When the input bit 0 comes, the output will be 0, 0 from the encoder structure, and the next state will also be 0, 0. But when input 1 comes, the output will be 1, 1, and the next state will be 1, 0. So you have to draw the trellis diagram for all these states, right? As I'm trying to explain you. So this is the trellis diagram which is drawn. You go from this point to this point, then this point, then T1 to T2, T3. You have to draw the complete trellis diagram. So this trellis diagram actually explains the flow of data as per that encoder structure. And this trellis diagram is known to the transmitter also and receiver also, because this trellis diagram is based on the encoder structure. There is nothing that I am trying to decode or anything. It is only based on the structure of the encoder, this trellis diagram is made. When 101 as the input bits are there, so these are the branch words that we will get, and 00 are the tail bits to flush out the data from the shift register to make the contents of the shift register to 00. That means the shift register will come into a 00 state. All right, now comes is the let me come to the decoding part. I will come, as I said, I will come back to the explanation of the Viterbi algorithm, but let me start from here, from this example. Now, what message vector we have? We have 101. What is the code word that will be generated? 11, 10, 00, 10, and 11. This 11, 10, these are known as the branch words. This 11 is one branch word, second branch word, third branch word, fourth branch word, and fifth branch word. And combined, all these branch words will form the code word. Right. So this code actually message vector comes at the input of the encoder, but we will send this code word. Instead of sending 101, we will send this full code word, right, after doing the coding. Now, the code word passes through the channel. It gets affected with noise. There may be some errors. The errors means error means 1 can change to 0 or 0 can change to 1. So that's why we have incorporated the channel coding, so that we can take care of the errors, we can detect the errors, and we can correct the errors. So now let us say that what we receive at the receiver is 11, 10, 11, 10, and 01. Forget about this U. We don't know at the receiver, sitting at the receiver, we don't know what was transmitted, but we received this. Now we have to detect the errors and we have to correct the errors, right, based on this, and we have to extract the message vector out of this coded sequence that is received. So that is actually the decoding of the convolutional codes. Now for that, you have to, at the receiver, you will have to draw a receiver trellis based on the Hamming distances. So let us see how to draw the trellis. Now, this is the trellis drawn. So what is the first branch word received? It is 11. Look at, this is the trellis, transmitted trellis. Some branches are not shown here as per this diagram, right? But the trellis remains the same. The shorter version of the trellis diagram. So let me come to the, so this is my trellis diagram, which is known to the transmitter also and the receiver also. Now the received branch word is 11. The first received branch word is 11. So assuming that, receiver will also assume that the initial state of the encoder is 00. So it will start from here. Now receiver will think whether 0 was transmitted, because he has to make a decision. He has to decode receiver at the receiver, and the receiver has to decode whether 0 was transmitted or 1 was transmitted. So the receiver will make an assumption. First of all, it will make an assumption that 0 was transmitted. And if 0 was transmitted, the receiver knows 00 should have been the output. But received is 11. So what a receiver will do, it will find out the Hamming distance between the outputs. Hamming distance means number of bit positions the output differs from the received branch word. So it is 00 here, it is 11 here, so it differs by 2 bit positions. So Hamming distance is 2. So the receiver trellis puts the Hamming distance of 2 here, right? Then it assumes that, okay, if 0 was not transmitted, certainly 1 would have been transmitted. If 1 would have been transmitted, no, then what is the output? Output should have been 1, 1. And what is received? Received is 1, 1. So what is the distance between the two? 0. So we put a distance of 0 here. So from this 0, 0 state of the encoder, the trellis can go to either this state or this state. And these are the Hamming distances mentioned. All right. Then it starts from here. If the initial state is 0, what is the second branch word received? Second branch word received is 1, 0. Now it assumes that if 0 was transmitted, then what is the output? 0, 0. But what is the received output? It is 1, 0. What is the Hamming distance? 1. So we put a 1 here. But if sitting at this state, if 1 was transmitted, right? So look at this trellis. If 1 was transmitted, what should have been the output? 1, 1. But what is the output? 1, 0. So what is the Hamming distance? 1. So we put a Hamming distance of 1 here. Similarly, we will go for going from this branch to this branch. If 0 was transmitted, output would have been 1, 0. But what is the output? 1, 0. So the distance is 0. All right. So sitting at this place, right? If it from the start it goes to this place, and if 1 is transmitted, what should have been the output? 0, 1. But what is received? 1, 0. So what is the Hamming distance? 2. So we put a Hamming distance of 2. In this way, we keep on putting the Hamming distances. At T1, we will take this branch word. At T2, we will take this branch word. At T3, we will take 1, 1 as the branch word. At T4, we will take 1, 0 as the branch word. And T5, we will take 0, 1 as the branch word. And we will put the Hamming distances, right? And we will proceed further with the trellis diagram. Now this is done at the receiver. Receiver can do this because receiver knows the general trellis structure, and then it will try to compare what is received. Okay. So this is in this way, all the distances will be put. Now, what is Viterbi algorithm? Where comes the innovation? Viterbi algorithm says that, as I said, if you do not implement the decoder with the help of Viterbi algorithm, then there is huge amount of computations required, huge amount of comparisons need to be made, right? With the received code word will have to be compared with every possible code word. So it would happen 2 raised to the power L. And that type of search is known as brute force approach, which is not possible, which is physically not possible. It's not implementable, right? Then where does this Viterbi algorithm come into picture? Now Viterbi says, this is very important. Viterbi says these are the paths, going from one state to the other, then to the other, then to the other. These are the branches, or we call these as the paths. Viterbi algorithm says that if in a state, you look at time t4 and look at this first state, Viterbi algorithm says that if 2 paths are entering into one state, right? So which are the 2 paths entering into this straight path? One path is the straight path, and the second is going from here and then going from here. 2 paths are entering into this state. Now Viterbi algorithm says if 2 paths are entering into one state, then one of the paths will survive. The second path will diminish. It will not lead to any significant output. So in this way, we can keep on rejecting the paths which are not surviving paths. Now, the question is that on what basis we should say that this path is a surviving path and the other path is not surviving path. So we are writing here the branch metric, or the distance between the branch word and the received branch word, and this is known as this distance 2 is known as branch metric. This distance 1 is also known as branch metric. This distance 2 is also known as branch metric. All right. And for the implementation of the Viterbi algorithm, the algorithm will also keep adding these branch metrics at every branch. So when it reaches to this state where it finds that two paths are entering into this state, so one of the paths will have to be rejected. One of the paths will not survive. And what is this? What is the total branch metric? And this total branch metric we will call also as the state metric, right? What is the state metric at this point? It is 5. So what is the state metric for the other path? It is 0, 0, and 0. So other state metric is 0. One path has a state metric of 5. The other path has a state metric of 0. Which will survive? The path with the maximum state metric will survive. The path with the minimum state metric will survive. All right. So if I show you here, so it is shown here, this path will not survive. Rather, this path, which is going from, which has a state metric of 0 for this state, this path will survive. And the path with a state metric of 5 will not survive. That means out of the two paths, whichever is having the minimum state metric, that will survive. So this is the innovation. Looks like very simple innovation, but actually it is mathematically proven also. This is maximum likelihood detection. This can be proven to be equal to maximum likelihood detection. But I am trying to explain you based on the graph, right? And you have to solve the questions like this only. How to solve the question? You write the branch matrix on the complete trellis, and if you look at this state, no two paths are entering into this state. No two paths are entering into this state. But at this state, two paths are entering into this state. Because other states are not feasible. If an encoder has to be in one of these states, starting from T1, only the encoder is in 0, 0 state. So there is no point in considering the trellis for the other states, right? But when you reach a time T4, at this point, two paths are entering into this state, so which will survive? The path with the minimum metric will survive. So this will survive, and this path is outrightly rejected. Now come to this state. What are the two paths which are entering? One is this path, 2, 1, and 0. What is the other path? 2, 0, and 0. So one path has a state metric of 3, the other path has a state metric of 2. Which path will survive? The path with state metric 2 will survive. Let me show you. Okay. So this path, it is rejecting. The path, this 2, 1, and 0, this path is rejected. And which path entering into this node will be survived? 2, 0, and 0. In the same way, we will reject the paths, one of the paths for this state and one of the paths for this state, right? So when you do the rejections, then you will see that, okay, in this actually there's, when you do this rejection and you start from this point again, when you start from this point again, when 0 will be there, this is the next state will be 0, 0, the next state will be 0. So what is the Hamming distance at T4? What is the, let me show you, at T4, what is the branch word? It is 1, 0, right? But at T4, what should have been there? At T4, if the input is 0, then 0, 0 should have been the output. But it is 1, 0. So what is the branch metric? The Hamming distance is 1. So it goes there. The point is that from this point onwards, For every node you will see, because in this diagram some of the paths it is automatically rejected, and then the final trellis diagram is shown. But when you will draw yourself, you will see that after this T4, at every node, two paths will enter every time. One of the paths, so what is the state metric for this path? 2, 1, 2, and 1. This will be, though 6 will be the having distance, 6 will be the state metric. But if you go from this side, it is 0, 2, then 1, 3, then 1, 4. So when it enters, when you look at this point, two paths enter at this point, and one has a metric of 6, the other has a metric of 4. Naturally, this path will survive. So we can show, in the final diagram, I can show. Okay, this path, this 1 minute. This is 1, right? This is 1, 2, and 2, 4. Okay. I will share you. Let me leave this diagram. I will show you from the book. Just wait for 1 minute, please. Let me open the book actually. I will share the book. Well, I'm not sure. I took these slides from somewhere, but let me show it from the book actually. Okay. Just wait for 1 minute, please. Let me open the book. Then we can. Okay, let me show you the complete trellis structure, and then we can an example. So let me stop sharing this and let me share you the book. So let me see who are the participants. Okay, Kirti, Varun, Kirti, Varun.
Yes, sir.
Are you able to see? I have shared the book actually. Are you able to
Yes,
see?
sir. Yes, sir.
Fine, fine, fine. So let me show you the decoder trellis. Okay. So this is the trellis, right? Receiver trellis, and these are the branch matrix. Now, how to do the rejections, we will see. Okay. At this point, let us look at the final, let us look at this node. Let us look at this node at T6, right? You, of course, you will keep on rejecting the path. Look, because I cannot draw on the board to explain this thing now, but you will have to understand my point to understand this part. So my point is that look at this node, and two paths are entering at node at state 00 at time T6. Two paths are entering. So one of the paths has to be rejected. And we will see the state metric here. What is the state metric? For the first path, it is 2, 1, 1, 1, and 1. What is the state metric? 6. 2, 1 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, 6. So 6 is the state metric for one path. What is the other path? The other path is trace back. It goes from here to here. What is the state metric? 1. What is the branch metric? 1. It goes from here to here. The branch metric is 0. Then it goes from here to here. What is the branch metric? 1. It goes from here to here. The branch metric is 2. And it goes back here to here. The branch metric is 0. So 0 plus 2 plus 1. Then it goes to 0, right? So 0 plus 2 plus 1 plus 0 and plus 1. This 1 plus 0, 1 plus 1, 2 plus 2, 4. One path has a path metric of state metric of 4. The other has a state metric of 6. Let's look at the final diagram. So this is the final diagram, right? At this point, actually, it's not okay. That's fine. We can use this as the explanation. All right, this will be okay. So starting from the initial point, it is 0. One path branch metric is 2. The other branch metric is 0. We will write the state matrix here. State metric is 2. State matrix for this path is 0. Let's look at the second diagram. So it goes from here. What is the state metric for this? It is 3. The state metric of this is again 3. For this path is 3. State metric of this path is 2. State metric of this path is 0. Correct? This is how the state metrics are written. So you start from here. 2 plus, now at T4, you look at T4. At this node, 2 paths are entering. One is this path, the straight path. The other is this path. Right. So what is the state metric? 2 plus 1 plus 1 is 4. What is the state metric for the other path? 2 plus 1 is 3. So that is why this 2 plus 1 path is the surviving path, and the state metric is updated to 3. It will not take the state metric as 4. It will take the state metric as 3. Look at this node. At this node, 2 paths are entering. One is 2 plus 1 again 4. The other path is this 1 plus 2 and 0. So the other statement, so this path will survive. It is 3. The other path will be rejected. Look at this point. At this point, again 2 paths are entering. This branch metric is 2 plus 1 plus 2, 5. And this branch metric is 0, 0 and 0. So state metric 0 survive and this path survives. The other path is rejected. And similarly, it is for the second. So the point that I'm trying to mention is that Viterbi algorithm says one of the paths will not survive. The other path will be surviving path. Who is the surviving path? With a lesser state metric. All right. So let's look at further diagrams. If you proceed further at T5, if you see, right, this 2 paths will terminate at this node. This is with one is this surviving path. Now this path we have rejected. This horizontal path, if you remember, this path of 2 plus 1 and 2 plus 1. Sorry. This path of 2 plus 1 is rejected, right? So we will reject the paths, and at T5 2 paths are entering. So these are the two paths. At T5 2 paths are entering. One is this path with 1 plus 1 plus 2, 4. The other path is 1 plus 0 plus 0 plus 0. So this path will survive. 1 plus 0 plus 0. What is the updated state metric? 1. And look at this node. What is the surviving path? 2 paths are entering. 1, this 1, this 1, this 2, and this 0. So the state metric is 1 plus 1 plus 2, 4. The other path is this 1, 0, 0, and 0. So that means state metric will be 1. So let us look at the ultimate trellis diagram. What is the ultimate trellis diagram? Because we are considering 5 branch words received. So at point T6, the trellis will end, and we will see then the final state matrix. The final state matrix are 1 plus 2 plus 2 and plus 2. We will then trace back. Please mind it. We will then trace back from one of the nodes. From which node we have to trace back? We have to trace back with the minimum state metric node. So what is the minimum state metric? This point is the minimum state metric. And we have to trace back from this point. Now tracing back, it is now decoding. Tracing back, going from this node to this node, what is the input 0? Going from this node to this node, going from this node to this node, no, the dotted line is 1. Going from this point to this point, let me get the final output. What is the final output? Or you can start from here. Actually, dotted line, it is representing with 1. I suppose it is representing dotted lines with 1. Let me see also. Okay. Dotted line, it is represented with 1. Right. So when the dotted line is being represented with 1, here you can see is facilitated by having note that the first bit was not decoded. Okay, so what is how to decode it? So this is the minimum state metric. This node, from this node to this node, it is 1. From this 0 is the distance actually. It is writing the distance. So dotted line actually gives me what input was there, what input could have been there. Mute kar lo, please. Going from this point to this point, the input is 1. Going from this point to this point, again the input is 1. Going from this point to this point, it is 0. This 1, this is 1. So what is the data? What is the input data that we are considering? It is 11011. For this example, right? What is the input data that we are starting with? 11011. And what we have decoded, how to do the decoding? Let me explain you the decoding part. 1101. At the trellis diagram, you should get 1101. So as I said, once you reach to T6, you have to stop and you will then have state matrix. 4 state matrix will be there, 2, 2, 2 and 1. You have to trace back from which state matrix? From the node which has the minimum state matrix. What is the minimum state matrix? Minimum state matrix is 1. So you start from this point. Go and trace back. Going from this point to this point, right? So this is represented by a dotted line. So that means it is 1. So take it as 1. Going from this point to this point, again it is 1. Please don't confuse with this 0 and 1 put here. These are the distances. Dotted line tells me that input is 1. The bold line tells me that the input is 0. So this input is 1. This input is again 1. Now this is bold line. This is 0. This is again dotted line. This is 1. This is again dotted line. This is 1. So what is the decoded data? 1, 1, 0, 1 and 1. So that's the data that was actually transmitted. If you see in this example from the book that I have taken, the input data was 11011. So we have been able to decode the data perfectly. Let me put the things in perspective and let me try to explain the things once again. This is the data, 11011 is the data which was to be transmitted from the transmitter. But we put channel encoder in the path, convolutional channel encoder in the path. We say that we will introduce some more bits so that if some error occurs at the receiver, we can detect and correct the error. And this is the code word which we actually transmitted. Instead of transmitting 11011, we transmitted this code word. But while it traveled through the channel, the received code word was 11010110 and 01. So, but we from this point to here, we can see that there is an error, but actually we don't know the error. When this Z sequence is received at the receiver, because sitting at the receiver, we don't know what is U. Sitting at the receiver, we only know Z. We don't know which bit is in error, right? So we try to decode it. We try to decode based on the decoded trellis, right? We start making but we know the transmitter trellis. We know this trellis structure based on the structure of the based on the structure of the channel encoder. Let me show you. We know this trellis. This trellis we know. And we start comparing the received branch word with the possible branch word, right? And we then represent this thing using the Hamming distance. Let me come to this. Yes, we represent using the Hamming distances. We put every distance, right? Then Viterbi comes here into play. Viterbi algorithm comes into play, and it says that when two paths are entering into one of the nodes, one of the paths will be surviving. The other path will not survive. Now, which path will be surviving? The path with the minimum state metric will survive. At this point, what is the state metric? 2 plus 1 plus 1. The state metric is 4. For this path, what is the state metric? 1 plus 2. 3 is the state metric. So this path will survive and this path will be rejected. That's what is shown in the diagram. This path is rejected and this is the final, this is reaching to, this is at the same time rejecting the paths. So what is the final decoder trellis? This is the final decoder trellis. At this point, final decoder trellis, the nodes will have their state matrix, updated state matrix. We have to trace back now. Trace back from which node? That node which has the minimum state matrix. So this node has the minimum state matrix. Start tracing back. You go from here to this, from this node to this node. Since it is connected with a dotted line, so that means it is 1. Again, this is connected with dotted line, it is 1. Again, it is connected with bold line, so this is 0. Dotted line and dotted line. So this is 1, 1, 0, 1, 1. That's the decoded message from the decoder, and that's what we know that this was actually transmitted 11011. So in the exam, you will not be given this message sequence and you will not be given this U. But what will you be given? You will be given the encoder structure, right? So that you can draw the trellis diagram, the transmitter trellis diagram, and you will be given this received sequence. From the received sequence, you will be asked to decode it, to decode the message vector. So how will you decode? You will first draw the transmitter trellis from the encoder structure. Then you will draw the receiver trellis based on these Hamming distances. And then apply the Viterbi algorithm, where you will be rejecting the paths which are not surviving and ultimately reach to the final stage. When you reach to the final stage, you have to trace back. Trace back in terms of you will have to start from the node which has the minimum state metric. So once you do that, right, you will be able to decode your, so this is the final trellis, receiver trellis, after rejecting all the paths which are not surviving. So you reach to this trellis, and you will see that now at this point, at every node, you will have only one path entry. So and every node will have a state metric. You start from the node having the minimum state metric, trace back, you will be able to decode the data. So this is known as Viterbi algorithm, used to decode the convolutional codes. Convolutional codes, in the exam, you will be given the encoder structure. Try to solve the questions which I have given in your assignment 2, because I have finished with the linear block codes also, and I have done the convolutional codes also. Please try to do the questions, and if you find any difficulty, then you please ask me, right, if any doubts you have. At present, if you have any doubt, you can ask. Or yes? Okay, I will. Yes, please go ahead. If somebody has any doubt, please ask. Okay, then I will end the lecture, and I will share this video also on LMS, on YouTube basically, but link is available on LMS, and I have already shared the notes. And the book I'm referring is Bernard Sklar. I have already sent you the book also. Thank you.